We're going to sketch the graph of r equals 1 plus 2 times the cosine of theta. We're going to do it a couple of different ways. We'll get the same graph. But what I want to remind you of is that this is one of the types that we saw before, as I called it a common type. And when we see 1 plus 2 cosine of theta, we can see that a is 1, b is 2, a is less than b. Therefore, we're going to have a limacon with an inner loop. Having recognized that, we can set up a theta r table. Now this is a little weird because points on the plane have the form r theta, but theta is the independent variable. So when I set up a table here, I have theta as the input on the left, r is the output on the right. Knowing that this is a limacon with an inner loop, I really only need to know what's going on the x and y axes. So for theta, I'm going to use 0, pi over 2, 3 pi over, nope, I skipped pi. Theta pi over 2 pi and 3 pi over 2. Of course, 2 pi corresponds to theta equals 0. You can confirm that when theta equals 0, r equals 3. When theta is pi over 2, r is 1. When theta equals pi, r is negative 1. And when theta equals 3 pi over 2, r is again 1. We can plot these points. 0, 3 is on the polar axis at a radius of 3 units out from the pole. Pi over 2, 1 is on the vertical axis on a circle of radius 1. Pi negative 1 would be on what we would call the negative x-axis, the angle theta equals pi, but the radius is negative 1. And so instead of plotting it at 1, we jump over the pole and it ends up on the positive side of the polar axis. And then finally 3 pi over 2 gives us a radius of 1. And then we do our best to connect these using a nice curve. There we go. That line is incredibly thick, so I'm going to fix that. That's better. Now, folks, sometimes people graph these, and they're doing their best. I know they are. But they graph them and then things look like kind of triangular, kind of sharp, or really asymmetrical. I'd like you to do your best to generate curves that look like what you see in the textbook. Now I said we were going to graph this two ways. The other way is to consider in the xy plane the equation y equals 1 plus 2 times the cosine of x. Now, when I say in the xy plane, I mean using a rectangular coordinate system. And the goal of this is going to be to translate the graph that you've come to know and love for a function like this and see how it translates into the polar plane. I have here marks on the x-axis that correspond to the quadrantal angles, pi over 2, pi, 3 pi over 2, and 2 pi. And then marks on the y-axis indicating the scale. I've gone from negative 1 up to 3. This cosine function, y equals 1 plus 2 cosine x, has a coefficient of 2 on the cosine, that'll be the amplitude, and then a vertical shift of 1. And so what I tend to do is I'll draw a horizontal line at that value of the vertical shift. I call that the baseline. It's kind of like the new 0, it's got moved up 1 unit, right? Then I know that the cosine curve starts out at a maximum, so I'll plot it at 0, 3, and then it hits its baseline. And then at pi, we'll have a minimum at negative 1, again, baseline at 3 pi over 2, and then a maximum at 2 pi. Connecting these with a nice smooth curve will give me the cosine function that we're all familiar with, right? Now, the angles from 0 to pi over 2 in this xy plane correspond to the angles from 0 to pi over 2 on the polar grid. So we go from 3 down to 1. And so in the polar grid, that corresponds to 3 down to 1 for the radius. Continuing on, we go in the xy plane from 1 down to the x-axis. Now that'll correspond to this little itty bitty bit here where we've gone from 1 down to the pole. Remember, the radius at the pole is 0. Then on the xy plane, we have this bit that dips below the x-axis, and it goes down to a depth of negative 1. That below the x-axis, folks, that's where this little inner loop is coming from on the polar grid. Okay? Then we go from the x-axis up to 1, And that's going to correspond to this little, again, this little itty bitty bit that goes from zero, a radius of 0 to a radius of 1. And then finally, we finish up going from 1 to 3. And that'll give us this last part here going from 1 to 3. This was kind of unnecessary in this particular case because we got what we needed knowing it was a limacon with an inner loop and r theta, but this can be a very useful process in the event that we don't recognize a function right away.